The web is colossal, so much that light has been going for more than 13 billion years. The universe has been creating, and hence the light has been loosening up for the most faraway universes we're recalling in time, almost to the Big Bang. The boundlessness of the universe could appear to be gigantic, yet every single piece of it began from what we allude to as the singularity. This is the way we decipher the hypothesis of how things came to be. In any event, the James Webb Space Telescope, JWST, has uncovered titanic mysteries about the birth and development of the universe, leaving us befuddled. Lofty physicist Brian Cox has declared that the striking revelations made by the JWST could reshape our point of view on the universe in general. Go along with us as we jump into these new, wonderful disclosures that promise to disturb our comprehension. The James Webb Space Telescope, named after the perceived NASA chief James E. Webb, remains as a wonder in present-day space exploration. This telescope represents a monstrous technological jump forward from its ancestor, the Hubble Space Telescope. Thanks to a helpful exertion between NASA, the European Space Agency, and the Canadian Space Agency, the JWST outperforms the capacities of its representative, using cutting-edge technology and a design streamlined for studying the universe exhaustively. Unlike the Hubble, the JWST conveys clear and sharp pictures of distant celestial bodies, working mainly in the infrared range. This exceptional feature allows it to look through enormous dust clouds and capture glorious objects that were previously stowed away from our view. With its epic 6.5-meter primary mirror, produced from 18 hexagonal fragments, the JWST diminishes the Hubble's mirror in size. Positioned around 1.5 million kilometers away from Earth at the second Lagrange point, L2, it circles the Sun in a place of balance with Earth, ensuring a consistent and stable perspective of the universe while filtering the far-off corners of space, looking at light years away. This also involves a type of time travel, as the JWST uses infrared instruments to observe celestial objects and events from billions of years ago. The light produced by these objects, due to the expanding universe, undergoes a redshift, moving from the visible range to the infrared range, or longer wavelengths. Fortunately, the JWST can recognize infrared light produced by celestial bodies at extreme distances, enabling researchers to study the birth of stars, explore the universe's development, and examine exoplanet climates. Its latest amazing revelation includes recognizing a tremendous mass of galaxies at the edge of the observable universe. This finding challenges the validity of the theory of how things came to be, prompting a reassessment of our key cosmological assumptions to better understand how we arrived at this point. To better comprehend how we arrived at this point, let us take a brief journey through the history of space exploration. Early developments, like those of the Greeks and Chinese, laid the groundwork for understanding planetary movement by observing celestial bodies. Newton's laws in the 17th century provided a theoretical framework for space travel. In the mid-20th century, Edwin Hubble, a prestigious space expert, made crucial discoveries in cosmology and observational space science. His observations revealed that distant nebulae were independent galaxies, far beyond the Milky Way, changing our understanding of the universe's size and expansion. Hubble's law showed that galaxies farther away were retreating at higher rates, providing evidence for the universe's expansion. The post-World War II era marked the beginning of the space race, with the Soviet Union's Sputnik in 1957 as the first artificial satellite in orbit, Yuri Gagarin's orbital flight in 1961, and the Apollo 11 moon landing in 1969 as landmark achievements. Fast forward to 1990 when the Hubble Space Telescope was launched, providing stunning clarity and historic insights into the universe. The transition from early observations to the technological marvel of the James Webb Space Telescope highlights the ongoing evolution of our understanding of the universe. The Hubble Space Telescope, HST, captured the famous pillars of creation image in the Eagle Nebula, revealing a stellar nursery formed by massive clouds of gas and dust. Another key achievement was the Hubble Deep Field, which captured thousands of galaxies in what appeared to be an empty patch of space. The HST also delved into exoplanet environments, pinpointing elements like water and organic molecules in distant worlds, highlighting the possibility of habitable zones beyond our solar system. Following the discovery of the closest observed supernova, SN 1987A, it shed light on the light curve of massive stars. These accomplishments cemented the Hubble Space Telescope's legacy as a foundation of modern space science, captivating the world with its stunning astronomical discoveries. Its successor, the James Webb Space Telescope, JWST, was launched to build upon the technological advancements and lessons learned from Hubble. One example is our understanding of the universe's beginnings, explained today by the prevailing theory of the Big Bang. Around 13.8 billion years ago, the universe began as a hot and dense singularity, rapidly expanding and leading to the formation of matter, energy, and fundamental forces. As the universe expanded, it cooled, leading to the formation of atoms, stars, galaxies, and the structures we observe today. The theory of how things came to be also explains the cosmic microwave background, CMB, radiation, part of the large-scale structure of the universe. Despite its broad acceptance, the Big Bang theory faced skepticism and challenges in its early years. Alternative models, like the steady-state theory, proposed a universe without a specific beginning. Concerns emerged about the evidence supporting the primordial singularity, the expansion process, and observed anomalies. Many of these issues were addressed over time, with much of the evidence coming from the discovery of cosmic microwave background radiation in 1965, aligning with Big Bang predictions. Space missions like COBE and WMAP, along with technological advancements, further supported the theory. With exact estimations of astronomical microwave foundation radiation coordinating hypothetical forecasts surprisingly well, enter the James Webb Space Telescope, outfitted with cutting-edge infrared instruments equipped for looking through immense residue mists, working mostly in the infrared reach. The JWST catches the most seasoned light in the universe, noticing objects shaped soon after the Big Bang. Its infrared capacities permit it to zero in on star-forming areas, heavenly nurseries, and the introduction of stars that are obscured from optical telescopes. Infrared light, with longer frequencies than apparent light, can enter interstellar residue mists, defeating a restriction of the Hubble Space Telescope. The JWST can identify cooler items discharging basically in the infrared, making it ideal for concentrating on peculiarities like exoplanets, earthy-colored midgets, and far-off worlds. As divine bodies move away, their produced light stretches, causing a redshift. The JWST's infrared capacities identify these redshifted signals, catching light from the early universe and giving experiences into its development. Events like black hole formation or new star births predominantly discharge in the infrared, further expanding the JWST's observational limits. The telescope can investigate peculiarities that would otherwise remain stowed away, either truly or indistinctly. The JWST supplements optical telescopes like Hubble by offering upgraded responsiveness and the capacity to recognize infrared radiation. This ability permits it to peer further into space and dive deeper into infinite history, uncovering stowed-away cosmic mysteries and providing a more extensive perspective on the universe's improvement. The JWST fills in as our window into the prior phases of enormous development. As of late, it uncovered something so remarkable that it could prompt a reassessment of the whole cosmological model of the universe. We have tracked down tremendous masses of universes at the actual edge of the noticeable universe. These antiquated universes existed 200 or 300 million years after the Big Bang, marking the beginning of the universe. The surprising part is that we're uncertain how such huge designs formed so early in the universe's history. This discovery could lead us to re-evaluate our comprehension of the arrangement and development of galaxies in the early universe. Concentrating on early galaxies is essential for unraveling the mysteries of the universe's beginnings. The JWST can provide insights into how galaxies, stars, and planetary systems formed and developed over billions of years. These observations also add to broader inquiries about the crucial nature of the universe, including its composition, structure, and the forces overseeing its development. While the Hubble Space Telescope was noteworthy for its time, it had limitations in observing the early universe. Its primary constraint was its inability to penetrate infinite residue and recognize the infrared light radiated by old galaxies. Earlier telescopes depended on visible and ultraviolet light observations, making it challenging to investigate the early universe, where these frequencies are absorbed or distorted by infinite residue and gas. The James Webb Space Telescope represents a quantum leap in observing galaxies from the universe's outset. Unlike its predecessor, the JWST can observe heavenly items that formed within just a few 100 million years after the Big Bang. Utilizing its infrared responsiveness and advanced imaging capabilities, the JWST has uncovered an abundance of ancient galaxies, offering unrivaled clarity and detail in understanding the universe's complex history. Beginning discoveries from JWST observations have stirred waves in established cosmological models, providing detailed data that challenges several parts of prevailing theories. These discoveries are prompting cosmologists to re-evaluate core principles governing our understanding of cosmic development and structure. Discrepancies between observed data and theoretical predictions have sparked intense debates among scientists. JWST observations have revealed more galaxies in the early universe than expected by current models, suggesting a more complex and fast development process. Some observed early galaxies appear unexpectedly mature, challenging traditional models that predicted slower growth. The discovery of a large number of galaxies challenges the predicted distribution and organization of large-scale structures, uncovering a more intricate and denser cosmic web than previously thought. These observations raise intriguing questions and open avenues for further investigation. The presence of massive structures challenges early models of large-scale structure formation, prompting scientists to refine models for better explanations. Understanding how such large structures coalesced so early after the Big Bang presents a puzzle that requires an updated framework of cosmic development. At last, the James Webb Space Telescope provides phenomenal access to the early universe and is likely to open endless secrets. This breakthrough, alongside other revelations on the way, will reshape our conception of the universe's development, the introduction of stars, the formation of galaxies, and maybe even the very nature of dark matter and dark energy. The JWST revelations open new chapters in space exploration, promising exciting discoveries that will continue to shape how we understand the universe.